we'll start. Jason.
Okay, I've resumed the recording. So yeah, Tricia, whenever you're ready, you can start.
Okay, great. So thanks for having me, and I will talk. So coming to you from Eugene, Oregon, not that far away, actually. Oh, actually, before I even start, I'll give an advertisement. I think we're going to start a Pacific Northwest conference series in the next year for combinatorics, kind of like Triangle Lectures in Combinatorics. And maybe some of them will be online. So we'll be sure to let you guys know, especially about online ones. But anyway, today I'm talking about posets arising as one skeleton of simple polytopes, the non-revisiting path conjecture, and poset topology. And I was actually working with Carola Mazaros on a different project, and sort of one set of ideas leads to another. And this project ended up kind of sprouting out of that. Carola didn't think she should be a co-author, but I definitely am grateful to her for discussions. We have a joint paper on something called SB labelings, and this somehow is an outgrowth of that. But the other thing, I'm having a little trouble advancing the page. Let me make sure I can. I'm getting. Okay. So I don't know what was happening, but okay. So I'll review background and stuff. But I want to. So as a postdoc, actually, long ago at the University of Washington, I heard a lot of talks about polytopes from the standpoint of linear programming. And if you have a I'll review definitions, but with a polytope, that's something like, oh, you can't see me. I was going to hold something up. I'm actually gesturing, but I just realized that's useless to you. So I'll try to remember that. But anyway, a polytope is like a convex hull of a bunch of vertices, or it's an intersection of half spaces, as I'll say later. But anyway, so polytopes, a lot of interest in them comes from the world of linear programming. And I guess I'll give a little example here, but it motivates problems in combinatorics. And let's see, so what do I want to say to start? That there's this thing called linear programming that's important in operations research, and there's been a long interest over many decades in the complexity of linear programming. And I started to think that there could be interesting classes of polytopes that are related to partially ordered sets where linear programming would work especially well, and that one might be able to use Posset theory to explain give a little bit more understanding why linear programming works well in certain situations. So that's very vague, but okay, so linear programming, here's the setup. So you start with a real valued matrix A and real vectors B and C, and you want to look at the following. You want to look at the set of points X. So let's see, if A is an M by N matrix, then A is a linear transformation from Rn to Rm. Or let's say A is N by N, N by M. So it's a linear transformation from Rn to Rm. So Ax lives in Rm, and you fix a vector B in Rm, and you want to look at the set of vectors X in Rn such that A times X is less than or equal to B, where less than or equal means coordinate-wise, that each coordinate of Ax is less than or equal to the corresponding coordinate in B. So that's like the set of points you're interested in. And then you have some other vector C, and you want to figure out among all of the X that satisfy the system of inequalities, which X has the biggest dot product with the vector C. Or sometimes you'll want to ask which vector X has the smallest dot product with the fixed vector C. And there's actually a lot of real world problems that can be phrased like this. So the set of X where Ax is less than or equal to B is what's called a polytope in the event that this set of X is bounded. And if it's unbounded, it's a polyhedron or polyhedral complex. But so I drew a little picture there of an example of one of these sets X. set of X in green and purple with the arrows on it, and just, that just below that P. The point is that each inequality is a linear inequality, so it specifies some hyperplane in Rn where your points have to be on one side or the other. And since it's a weak inequality, you could be on the hyperplane. But so each inequality gives you a half space that X has to be within. And then when you have a whole bunch of inequalities you have to satisfy, you take the intersection of these half spaces. So, and you could picture that polytope, you have like a bunch of planes cutting it out, where for each plane you're on one side or the other of it, right? So, and each face of the polytope comes from one of these bounding planes. Right, so that's how you can think of a polytope as being the set of X given by these kinds of linear inequalities. Okay, and then I have a little example in the lower left there with a particular A and a particular B. And then we're looking at the set of vectors x1, x2 satisfying this inequality. So we want that negative x1 is less than or equal to 0, negative x2 is less than or equal to 0, and x1 plus 2x2 is less than or equal to 2. And that's going to give the little blue region in the bottom left, as that'll be the points in the plane that satisfy the three inequalities. So then what you do is you pick another vector C, like that red vector I've drawn in the bottom left, and you look at all of the points in your region, in your polytope, and say which point has the biggest dot product with C. And I've drawn a bunch of parallel lines where the dot product will be constant on one of those lines, and like you sweep across the polytope to see that it's that the dot product with C will be maximized at the, in this example, in the vertex of the polytope in the kind of lower right of the polytope. It's weird to talk about this without being able to point at things, but I hope it makes sense. So anyway, okay, so this is the kind of thing that linear programming is about. And so people want to find algorithms to figure out what point in your polytope maximizes or minimizes the dot product with C. To this end, it's handy to draw a graph. I'm denoting as capital G of P comma C, a directed graph on the one skeleton of P. So the one skeleton is the set of edges and vertices of the polytope. So that'll be a graph. Like I've drawn it in purple for my example P up above, that I gave at the start there. Anyway, so we have this graph, and then we put arrows on the edges in the direction that the dot product increases. And we want to talk about generic cost vectors, which is going to be ones where there are no ties. So whenever you have an edge, the two endpoints have distinct dot product with C. So does this make sense so far? So anyway, okay, so then the place where this is maximized is going to be the sink of this directed graph. It'll be the unique vertex that has arrows coming into it and no arrows going out. And there will be a unique such vertex in your polytope. And the unique, or if you wanted to minimize the dot product, that would be the source of the graph, the unique vertex that has only out arrows. And and a really classic method in linear programming called the simplex method just starts somewhere on this graph of the polytope and then, looks at the edges incident to that vertex and which are in and which are out, and picks one of the out edges and follows it. And you just greedily keep going along until eventually you get to the sink. And or alternatively, if you wanted to figure out where the dot product was minimized, then you would walk backwards on edges to find the source. And then the question is, how many steps do you have to take? In the worst case or in the average case. Okay, and just to show you how a real world problem fits in this setting, the traveling salesman problem is a classic. So here we have this graph here, picture V1, V2, V3, V4 as being cities, and then we have roads between the cities and the number of miles on the roads, so 1.1 miles or 7 miles or 8 miles, whatever. And the question is, how could a traveling salesman or salesperson starting at city V1, visit all 4 cities and come back to V1 again, traveling the smallest distance possible. So they could take the green route, or they could take the purple route or the blue route, and they get different distances. And then I've drawn those, I've depicted below those as vertices of those 3 routes as vertices of a polytope in R6, where I've picked, I've indicated with 1s which of the 6 possible roads we're taking, and with 0s, the ones we're not taking. And if you think about it, then the distance you would need for one of the routes would be the dot product of the corresponding vector. Like for the green route, to get the distance traveled, you take the dot product of the green vector with a vector whose first coordinate is 2.5 and the second coordinate is 8, and the third, let's see, so the first coordinate is the distance on the edge E12, the second coordinate is the distance on the edge E13, third is E14, E23, E34, or E24, E34. So that's set up so that we have this vector, let's see, it would be 2.5, 7, 1.1, 3.4, 8, and 6, that vector. Oh yeah, I've written it at the bottom. And if you take the dot product of that with any of these 3 vectors, you get the distance for that route. And if you take the convex hull of these vertices, that's called the traveling salesman polytope. And you can solve the traveling salesman problem by using linear programming to figure out where is the dot product minimized on that polytope. So it may sound like overkill, but for big problems, this could actually be a good way to solve the traveling salesman problem. But the issue is how long does it take you to walk on the polytope to find the min or the max? Okay, so quick background on polytopes. A polytope in R to the D is the convex hull of a finite number of vertices in R to the D, or equivalently, it's a bounded set that is obtained by taking a finite intersection of half spaces, where a half space is what you get by taking a hyperplane in R to the D and taking all the points on one side of it along with that hyperplane. Okay, so that's a polytope. And for us, that's going to be the kind of domain where we're doing these things, this linear programming. Now, a polytope is said to be simple if each of its so this is dual to what's called a simplicial polytope. You might have seen simplicial polytopes, but here's one way to define a simple polytope. A polytope is simple if whenever you have a vertex of your V of your polytope, oh, you can probably see my cursor, can't you? So moving around, hopefully you can. So a polytope is simple if for each vertex V and each collection of edges, E1 through ER, emanating out of that vertex. So for instance, this V and these 3 edges, E1, E2, and E3, whenever you have a vertex and a collection of R edges emanating out of it, then there ought to be a face that's R-dimensional that in your polytope that involves the vertex and all the edges. So this thing on the left here is a simple polytope, but this on the right is not a simple polytope because here, like we have this vertex and these 4 edges that, and if you take 2 edges that are opposite each other, then they don't give you a face of the polytope because they would give you a 2-dimensional face, but in fact it cuts right through the middle, and so it's not a face of the polytope. Does that make sense? Are there any question? So anyway, this is a super important definition for what I'm doing, that we want to focus on simple polytopes, okay? All right, and now going back to, let's see, so, right, that's going to be our setup, these kinds of polytopes. So going back to linear programming, a pivot rule when you're trying to solve a linear program is a method to choose for each vertex of your polytope when you have a bunch of edges going out from it, it's a method to choose which of them to take, as the goal is to get to the sink as fast as possible. So you might say, take the edge that makes the cost increase the most, or you might have some other rule. And people in operations research have done tons of work studying all different possible pivot rules to try to figure out which ones will get you to the sink fast. Key questions are, what is the typical complexity of the simplex method? And by complexity, I mean path length, by which I mean the number of edges traveled. And what's the worst case? And that's related to the diameter of the graph of the polytope, of the directed graph. So if there exists two vertices whose distance is 17, then for sure then the worst case is going to be at least 17. It might be even worse than that, because you might be foolish in which path you take to get from the one vertex to the other. Okay, so the Hersh conjecture, and that's spelled differently than my last name and no relation to me, was a big conjecture that people in linear, like Victor Klee and Combinatorics, and people in linear programming were interested in for a long time, is as follows. It says that given a d-dimensional polytope with n facets, where a facet is a maximal face, then the diameter of the one skeleton of the graph is at most n minus d. So, and we're going to denote this diameter by delta of dn. So that was open for a long time, but after many decades of lots and lots of effort, Francesco Santos finally found counterexamples to it using something called spindles. And you can see this would be relevant to linear programming. So spindles are polytopes where you have two vertices V and W, such that every facet of the polytope is either incident to V or incident to W. And his first counterexamples were huge. He had a 43-dimensional polytope with 86 facets where he could prove theoretically that the diameter was at least 44. And now I'm talking about the undirected diameter, and I'm not talking about any cost factor, just the actual diameter, the number of, for two vertices of the polytope, what's the farthest two apart where the distance is the fewest number of edges traversed to get from one to the other. But a related conjecture is called the non-revisiting path conjecture. And this is really going to get into what I'm going to talk about. So for the non-revisiting path conjecture says for each pair of vertices U and V in a polytope P, there exists a path from U to V that never revisits any facet after departing from that facet. Oh, this is tough to give this without being able to gesture, but let's see. So if you think about it, so, oh, something just switched. Let's see. Are you still seeing this full screen?
Yeah, but it's zoomed out. It's smaller.
I see. Oh, I see okay, I'm sorry. This is different from how I'm used to doing things. So in any case, okay, I didn't mean to do that, but okay, I can keep zooming in and it gets bigger. Sorry. Okay, so let's see. So the idea here, let's suppose you have a cube, okay? Now, if you're at a vertex, just a normal cube with 8 vertices, if you're at a vertex of the cube, then that's incident to 3 different facets, right? Now, if you traverse one of the edges of your cube from one corner to another, then you depart one of those facets because there's one of those facets that you leave, and now at the other end of that edge, you're in the parallel facet, right? So that's what I mean by departing a facet. So the conjecture is that for any polytope and any pair of vertices UV, that there exists a path from U to V that whenever it departs a facet, it never revisits that facet. So, okay, so, but in fact, if the non-revisiting path conjecture were true, it would imply the Hersh conjecture. And so the counterexamples to the Hersh conjecture also give counterexamples to this non-revisiting path conjecture. So the idea is that if you're in let's see, if you're in a d-dimensional polytope, then every vertex has at least d edges incident to it, and at least d facets incident to it. And let's see, so if there were two vertices whose diameter, let's see, so when you have a directed path from, let's suppose the non-revisiting path conjecture held, and so you have a directed path from U to V. Each time you traverse an edge, you will be departing some facet, right? There will be some facet that you're no longer incident to as you walk along the edge. And so if your diameter were bigger than n minus d, there'd be n minus d facets that get departed, because each of your n minus d steps departs a facet, but then at the end, you're still incident to d facets. So let's see, so the diameter, we claim the diameter can't be more than the number so let's see, if you had a path of length n more than n minus d, you would have departed more than n minus d facets, none of which you can ever revisit. But then at the end of the day, you'd be incident to d facets, none of which you've departed yet. So you'd have more than n facets total. Anyway, so right, so this this also is not true. And there's something even stronger that one might think might be true, that when you going back to this directed graph kind of a situation, like I show here, you could ask, is it possible to have a monotone? I mean, could it be that, let's see, so let me get this straight. So the strong monotone path conjecture says that there exists a directed path of length less than or equal to n minus d from any vertex v to the vertex maximizing the dot product with c for your cost vector c, with the cost increasing at each step. And that's also false. So so the fact that, I mean, right, that because of the Hersh conjecture failing, and actually this was shown to fail earlier, they're going to have to be longer directed paths than that. So sorry, but anyway, okay, so that's just background, but now let me talk about what our plan is, okay? Rather than, it's really hard to deal with all polytopes at once, I became interested in trying to come up with, I started to suspect that one might impose further conditions on impose some hypotheses on a polytope and on a cost vector C, so that something even stronger than the non-revisiting path conjecture would hold. And I started to suspect that there were some kind of reasonable conditions to impose on a polytope that, I mean, intuitively, people for a long time thought that things like the non-revisiting path conjecture should hold. But it doesn't. There's pathological counterexamples. So I just wanted to try to think of, well, could we give conditions that not only make the non-revisiting path conjecture hold, but something far stronger that would be really great for linear programming? And specifically, what I wanted was conditions on a polytope P and a cost vector C that would imply the following corollary, that would imply the following. That whenever you have, for each U and V vertices in a polytope P, that every possible directed path from U to V never revisits any facet that it has left. So what this kind of says is that you can't go wrong with linear programming. If your polytope and your cost vector had this property, that whenever you have two vertices U and V, and there's a directed path from U to V, that no matter which directed path you pick, it will never revisit any facets that it's left. This guarantees that all of the directed paths from U to V should be pretty short. So this would be great if this held, but it's a question, how often does this hold? But I have a conjecture for conditions on P and C that this should hold. And while the conjecture is still open, I have proven a corollary of this conjecture that is encouraging and some lemmas towards this conjecture. So now let me get to the types of conditions on a polytope that I think might make this kind of thing happen. And this will draw us into the world of posets. Okay, so G of PC is a directed graph, right? It's like you have your polytope P and your cost vector, a generic cost vector, and then you have these directed edges like I've drawn here in the direction the cost increases. We say that that the directed graph G of PC has the Hasse diagram property if this directed graph is the Hasse diagram of a finite poset. And just to say that down to earth, what that is equivalent to saying is that, so you can think of the arrows as being, say, you have an arrow from V1 to V2 that says V1 is less than or equal to V2 in the poset, and that it's actually a cover relation, that it's a minimal comparability. So to be a Hasse diagram, if V1 is less than or equal to V2 and V2 is less than or equal to V3 and so on and so forth, by transitivity, we'd have V1 is less than or equal to VR here, right? So we wouldn't need to draw a directed edge from V1 to VR because that's transitively implied by the others. So this is not what's called a Hasse diagram. So the Hasse diagram property says that we don't draw any arrows that would be transitively implied by the others. So we can't have an arrow from V1 to V2. So if we have a series of arrows like this, then there cannot possibly be an arrow from V1 to VR. So this here fails the Hasse diagram property. And then sadly, anytime you have a simplex, like this 2 simplex here, and any possible generic cost vector, the resulting digraph is going to fail the Hasse diagram property, right? But so it rules out a lot of stuff, but that's one of the conditions we're interested in. And there are lots of polytopes from operations research that don't have simplicial faces. So so we still could be okay. Here's an example of a polytope and a cost vector. So that's our cost vector where the resulting directed graph does have the Hasse diagram property. So here we're fine. If you look, we don't draw anything that's transitively implied by the other stuff. And in fact, this poset here, this directed graph is the Hasse diagram for the poset of subsets of 1, 2, 3, right? Like this here is the empty set. This is the set with just 3. This is the set with 2 and 3. This is the set with 1, 2, and 3. So this is a Hasse diagram. Right, so, and there's plenty of polytopes and cost vectors that do have this property. Now, the very first, I'd like to say the very first, so there's something called the Clementi cubes that are historically very important in operations research and linear programming, because these were examples found by Victor Klee and George Minty that showed how situations where the simplex method could behave really, really badly. And I want to point out that these fail the Hasse diagram property, which I take as a good sign for the Hasse diagram property helping us to hone in on polytopes where the simplex method may work well. So here's a Clementi cube. So here we have a standard cube, and sitting inside it is what's called a Clementi cube. So we've positioned the 8 vertices of the standard cube into weird positions. For what it's worth, I've written down here how to describe the Clementi cube with inequalities. This picture is basically copied from a figure in a very nice diagram in a paper of Gertner, Henk, and Ziegler. But yeah, so here we have our Clementi cube. And if our cost vector is 0, 0, 1, so it points straight up, then if you write arrows in the direction the cost increases, you'll see that if you started at this vertex, you could follow directed arrows like this and take a really long path to get from this U to this V. I mean, there's a shorter path, but if you weren't smart with your pivot rule, you might take this really inefficient path that actually visits all the vertices. But I'd like to note that this example also fails the Hasse diagram property, because here we have a face where we have a directed path. Well, clearly it fails it, like that. You know, that directed path, we would also be putting this directed edge, and so we fail the Hasse diagram property. But we already fail it within a two-dimensional face, which I find interesting. So, right, so that you can already see it in this local sort of way. So that's one of the hypotheses I'm going to want to impose, is that the G of P, comma C be a Hasse diagram in order to prove things. Now, let me give a couple interesting examples. The permutahedron, that's a polytope who's in Rn, whose vertices are gotten by taking the as your n coordinates, the numbers 1 through n written in the various orders. So we have n factorial vertices. Take the convex hull of those. So here's a permutahedron. Now, if we use the cost vector 1, 2, 3, 4, then this will be a Hasse diagram, and it's actually the Hasse diagram for the weak order. You can check, and I want to note that I'll say more about this later, but so you can associate to any partially ordered set, any finite partially ordered set, a simplicial complex called its order complex. And Paul Edelman proved for the weak order in type A that each open interval in weak order has order complex homotopy equivalent to a ball or a sphere, and Anders Björner generalized this beyond type A to other types. And I will say, what got me started in this project was actually trying to do Posset topology, and somehow that's going to tie in later with what we're doing. But anyway, this is an example of a polytope and a cost vector satisfying the Hasse diagram property, and so you can actually get any weak order this way. As such a one skeleton. You can also get Tamari lattices this way, and those come from taking the isosahedron and Lode's realization of it. So another famous family of polytopes, and make a good choice of cost vector, and you get the Tamari lattice as you get the Hasse. Your directed graph, your G of PC, is the Hasse diagram of the Tamari lattice. And there, the homotopy type was shown to be, every interval was shown to be homotopy equivalent to a ball or a sphere by Björner and Wax using non-pure lexicographic shellability. And that'll also tie in later. So those are some examples. The Clementi cubes, as I said, violate the Hasse diagram property, and they do so in a way that really seems to be at the heart of why linear programming works badly for Clementi cubes. And so our hope is that the Hasse diagram property, together with, we'll also assume that we have a simple polytope, would preclude this kind of inefficient simplex method. So here's a lemma that starts to be suggestive of why how the Hasse diagram property may help. We also like to focus on the setting of simple polytopes, which people in linear programming very often focus on simple polytopes because they can kind of deform things to get to that setting. Okay, so let's say you have a face F contained in a face G within a simple polytope where they differ in dimension by 1. So G has dimension 1 bigger than F. And we have a generic cost vector C so that the resulting directed graph is a Hasse diagram. Then this technical sounding lemma that's super useful says that there does not exist any pair of vertices V and W in your face F such that there's a directed path from V to W that stays in F, and also an outward edge, and an out. So because let's see. So let's see. So the purple thing is F. The blue thing is what you get when you throw in G. So you up the dimension by 1. And because we're assuming simple polytope, then whatever the dimension of F is, V is going to have that many edges emanating out from it. So in this example, F is 2-dimensional and G is 3-dimensional. So there'll be 2 edges out from V that stay in F, and then one additional edge out from V that is in G but not F. So okay, so what we're saying is that if dimension of F is 1 less than the dimension of G, it's a simple polytope, this is a Hasse diagram, then it's not possible to have a directed path in F, so the purple thing, from a vertex V to a vertex W, such that the unique edge outward from V that's in G but not F goes out from V to the rest of G, whereas the unique edge incident to W that's in G but not F points into W. Okay, so we say that cannot happen. And the idea is basically is something like the intermediate, or is as follows, okay? So as we walk along the path from V to W, each vertex we encounter has a unique edge incident to it that's in G but not F, these blue edges. And each of them either points out or in. If V points out and W points in, there's got to be some point in time where we switch from out to in. Here we're out, the next one is in. I mean, it could be we switch back and forth, out in a bunch of times, but there has to be some pair of consecutive vertices where we switch from out to in. We have a directed edge like this goes out, this goes in. We can prove that these 3 edges all belong to the same 2-dimensional face. And within that 2-dimensional face, we're going to have 2 directed paths from, like in this case, V3 to V4, one of which goes around like this, and one of which is this single edge. And voila, we violated the Hasse diagram property. So anyway, so the Hasse diagram property plus having a simple polytope is enough to preclude this situation. Now, a corollary of this is that whenever you have a face of your polytope that has either the overall minimal element of the poset, or the overall source or the overall sink in it, if your face contains the source or your face contains the sink, then directed paths that start out in your face can't leave the face and come back to it. So this is something kind of close to the non-revisiting path conjecture, but it makes this important assumption that you have either the overall source or the overall sink, but it's a step in that direction. But what it actually does is it shows that the counterexamples that you can get from this, that the counterexamples that Francisco Santos had to the Hersh conjecture with the spindles cannot possibly satisfy this Hasse diagram property. So it's possible this Hasse diagram and be a simple polytope. The issue is that because they were spindles, you could set up those 2 vertices that contain all the facets. You could set things up so one of them was 0 hat and the other was 1 hat. And then every facet would be incident to one or the other. And your polytope would have to, and then my results would say your polytope would have to satisfy the non-revisiting path conjecture, which it doesn't. And so anyway, we can show that at least, so, my feeling is that having a simple polytope and a cost vector where you get the Hasse diagram property should allow you to evade the kinds of things that go wrong in Francisco Santos's counterexamples. So this is some evidence for that. And maybe in other counterexamples to the Hersh conjecture or to the non-revisiting path conjecture. But okay, so next ingredient, so I mentioned that we can't, so my conjecture is, I guess I should say this, that if you have a simple polytope and you have a generic cost vector so that the resulting directed graph satisfies the Hasse diagram property, then it's not possible for any directed path to ever revisit a facet after departing from that facet. And that's actually equivalent to saying that it's impossible for any directed path to revisit any face after departing from that face. And that's because every face is an intersection of facets. So while that's still wide open, that conjecture, I want to prove a corollary of it, or tell you about a corollary that it has been proven. So for this corollary, we're going to make a further hypothesis, which makes things more restrictive, but it's where we can, but this is where we can say things. So we're going to focus not just on Hasse diagrams of posets, but specifically of lattices now. So a poset L is said to be a lattice if whenever you have two elements U and V in your poset, there's a unique least upper bound for U and V called the join, and a unique greatest lower bound called the meet, and denoted like this. So I would note that if P is a simple polytope and G of PC, this directed graph, is a Hasse diagram, that suppose you have something like this, you have an element X that's covered by U and covered by V, then one way to get some sort of upper bound for U and V, so an element that's bigger than both, is to look at the unique two-dimensional face that contains the edge from X to U and the edge from X to V, and look at the sink of that face, this S here. Well, for sure, there's going to have to be a directed path. So every vertex in the face is going to have a directed path that gets to S, which means that S will be greater than or equal to U and V. So S will be an upper bound for U and V. So you would sort of hope that S would be the least upper bound for U and V, but it's actually tricky for higher dimensional polytopes to prove things like that. But so this leads us to something called, we're going to call the pseudojoin in a polytope. So let P be a simple polytope with a generic cost vector C. Suppose G of PC is the Hasse diagram of a poset L. And let's say X1 through XR are elements of L that all cover the same element U. So we have an element U, and then we have directed edges to all these things. Then, okay, so, and U, this less than here means that U is less than V with no possible intermediate elements. So it's a cover relation. And we're going to say AI is an atom of, so the closed interval from U to V is the set of poset elements Z that are greater than or equal to U and less than or equal to V. The atoms AI will be the things that cover U, so the things right above U. So with all this language, then we'll say that the pseudojoin of the elements X1 through XR, when you have something like this, is going to be the sink of the unique R-dimensional face of our polytope that contains all of these edges, right? So we have R edges. If it's a simple polytope and they're all emanating out from U, there should be a unique R-dimensional face that contains all of them. Its sink is the pseudojoin. That'll be an upper bound for all these things. And then the only question is whether it's the least upper bound, if we had a lattice. So I haven't yet assumed it's a lattice. I'm just saying, even for a poset setting, then we can talk about this being an upper bound, which we call the pseudojoin. So here for this U and this X1 and X2, the pseudojoin of X1 and X2 would be this with respect to U. Okay, so so given a simple polytope P and a generic cost vector C, where this is a Hasse diagram of a poset, if S and T are distinct subsets of the atoms of some interval, then the pseudojoin of S has to be different than the pseudojoin of T. So that's a result. And in the case of that's the overall atoms. But in the case of a lattice, this also holds for each interval. So if you have the interval from U to V in your lattice, and you look at any two different sets of atoms covering U, if they're distinct sets of atoms, they have distinct pseudojoins. And a corollary of this is that the subposet of just the pseudojoins of the various sets of atoms is going to be isomorphic to a Boolean lattice. So the poset of subsets of A1 through AN. And roughly the idea is to reduce to the case where you have a set S contained in but not equal to a set properly contained in a set T where they differ in size by 1. And then once you do that, you can actually use the lemma from before, this lemma here, to prove this. So we get this distinct set of pseudojoins. Okay, and let's see. So because the pseudojoin is an upper bound, then we know if we're in a lattice, then the least upper bound has to be less than or equal to every other upper bound. So there has to be a directed path from the join, from the least upper bound to the pseudojoin. Okay, so now what? So, okay, so now we get to one of this kind of one of the main theorems, and this is a corollary of our conjecture. So, okay, so here's a big theorem, or one of our main theorems. So let P be a simple polytope and C a generic cost vector, where G of PC is the Hasse diagram of a finite lattice. So that's this setup we're talking about, where we have a simple polytope, a generic cost vector, and this is we satisfy the Hasse diagram property, and we actually are going to further require it's the Hasse diagram of a finite lattice. Then the pseudojoin of any set of elements x1 through xr, covering an element u, actually equals the join of that set of elements. So just to give you an idea what this has to do with this non-revisiting path conjecture and the strong version of non-revisiting, here's a diagram, okay? So let's say we have this green two-dimensional face living within some high-dimensional polytope, right? And we have this vertex u that's covered by this x and this y. Well, an obvious candidate for what might be the join of x and y would be V, the pseudojoin of x and y. But what if that failed? You know, what if this theorem weren't true? Then it's not too hard to see that the join of x and y cannot possibly be anywhere in this green, well, I guess it could be in the green face, that's sort of a case, but what would have to happen is that there would have to be a directed path one possibility is that the join of x and y just isn't anywhere in the green face. It's out here somewhere, and we have like a directed path from y to it, and there's separate from that some directed path from x to it. And then because the join has to be less than or equal to the pseudojoin, there will also be a directed path from this to here. And in the course of all this, you'll see we have a directed path that departs from the green face and comes back to it. So this is right. So this, and on the other hand, let's say that x4 were actually the join of x and y. Then, well, we can get from x to x4 staying in the green face, but we can't get from y to x4 staying in the green face. So again, there'd have to be a directed path that left the green face and came back to it. So, I mean, with some work, you can show that if this strong non-revisiting thing held, it would imply this. But anyway, this actually does hold, and it's a lot of work to prove this. And even the two-dimensional, it's an induction on R, and the case with R equals 2 is actually perhaps the hardest case. There's a couple tricky types of induction involved, and there's kind of a mix of geometry and combinatorics. Like we utilize the fact that if you have 3 vertices that are shared by 2 different two-dimensional faces, then the two-dimensional faces have to be the same face as each other. So there is some geometry going on. But anyway, I see I'm running low on time. Let me get to the Posset topology part a little bit to show how it connects with that. So if we have a poset like this, here's a Hasse diagram of a poset. Its order complex is a simplicial complex whose vertices are the elements of the poset. And then whenever you have a chain of comparable elements like 0 hat less than A2 less than 1 hat, that gives you a face of the simplicial complex, where the number of vertices in the face is the number of elements in the chain. So like 0 hat less than A2 less than 1 hat gives us the 0 hat A2 1 hat 2 simplex, right, with those 3 vertices. So we get this abstract simplicial complex, and the Mobius function of the poset equals the reduced Euler for any interval from u to v equals the reduced Euler characteristic of the order complex of the open interval from u to v, so that topology is governing Mobius functions. And the Quillen fiber lemma is going to be relevant for what we're doing. And this is also Quillen theorem A from topology. It says given a map F from a poset P to a poset Q, actually we want a poset map, which means whenever U is less than V and P, f of u will be less than f of v and q. And we have a requirement that for each element little q in q, that if you look at the order complex of the set of things here that map either to q, little q, or something below it, that the order complex of that subposet of P is always contractible. Under those hypotheses, the order complex of P should be homotopy equivalent to the order complex of Q. This gets used extensively, for instance, in finite group theory to characterize group properties. Like John Sharestian has a lovely result that a finite group is solvable if and only if its poset of subgroups is shellable. Anyway, I guess that's not Quillen fiber lemma exactly there, but but anyway, we use so the results I've been telling you about with pseudojoins and all are going to allow us to get some poset topology results via the Quillen fiber lemma. So we have the following theorem. If P is a simple polytope and C is a generic cost vector such that our directed graph is the Hasse diagram of a finite lattice L, then the order complex of every open interval in our poset will be homotopy equivalent to either a ball or a sphere. And when it's a sphere, we can describe the dimension of the sphere by the number of atoms in the interval from U to V minus 2. And the point is we use a poset map that sends each element X in our interval to the join of the set of atoms of the interval that are less than or equal to X. And the point will be that join, by our previous theorem, that join is actually equal to the pseudojoin of those atoms. And we've proven that our pseudojoins of the various elements are organized into a Boolean lattice. And if you have a Boolean lattice, its order, if you take the proper part of it where you leave off the top and the bottom, its order complex is homotopy equivalent to a sphere, but if you put in the top or the bottom, it'll be contractible. And one way to see what I'm just saying is that a Boolean lattice is the phase poset of a simplex, and its order complex is the barycentric subdivision of that simplex. And so it's either we're taking the simplex with the interior left out and you get a sphere, or the interior in and you get a ball. But anyway, out of this, you can, as applications, you can get a unified proof that for the weak order and the Tamari lattice and also the Cambrian lattices, that every open interval has order complex homotopy equivalent to a ball or a sphere. And, you know, I was actually starting this stuff by doing poset topology, but then I realized that these same hypotheses seem to be, on the one hand, saying things about poset topology, and on the other hand, saying things about non-revisiting and efficiency of the simplex method under all possible pivot rules. So I started to wonder if maybe you could use poset topology to detect situations where the simplex method probably wasn't going to work well. But maybe the last thing I'll say is just that I'll reiterate this conjecture, that my conjecture is that if P is a simple polytope and G of PC is the Hasse diagram of a lattice, then no directed path can ever revisit any face that it has departed from. And it might be that you could do something kind of like this with non-simple polytopes too. It's just that the methods of proof that I can think of all involve that somehow having a simple polytope and having a Hasse diagram gives you a lot to work with. They go well together. It'd be interesting to understand the structure of the poset of pseudojoins for non-simple polytopes also. There might be classes of MV polytopes that this is relevant to, that could give other interesting posets. And I think I'll stop there. But sorry if I'm not used to talking without people being able to see me. Sorry about that, but thanks for having me.
Thank you.